quicker. All right, so the test is tomorrow. It is about 24, 25 multiple choice questions. There's a couple FRQ questions, so it'll be kind of short-ish. And there's no math, like I said, but don't let that fool you. Still, you got to prepare. So if you still need a paper copy of the review guide, you can come pick one up. I did post it on the Google Classroom along with the key. So check that out. Take some time to study and review today. All right. So definitely important to know the major difference between electric charges and magnetic poles. And probably one of the main differences is, first of all, they are not the same. They kind of interact with each other 90 degrees to each other, but they're not the same. And so probably the main difference that you need to be aware of is that charges can be isolated. You can have a positive charge all by itself. You can have a negative charge all by itself. But the north and the south poles cannot be separated from each other. If you have a north pole, you will always have a south pole. All right. So no matter what, even if you get down to the size of an atom, an iron atom will have a north pole and a south pole. Okay. Even a spinning electron will have a north pole and a south pole. So, so a magnetic field, this is almost like a vocabulary term. What is it? What's its source? But if you know what if you remember what an electric field is, and you remember what a gravitational field is, this shouldn't be too much of a problem for you. A magnetic field is just the area around a magnet that feels a force, or that you feel a force. The source, question? Okay, the source of a magnetic field, and this has been the foundation upon which everything has been building since last Monday or Tuesday. The source of a magnetic field is moving electric charges. Whether you've got a wire with a current going through it, and you have moving charges in that way, the current, or you have the spinning electrons that I talked about when I waved my hands. You've got moving electric charges, and that is the source of magnetic field. If you can remember that, that is a foundational key thing to remember. Okay, and again, if you're writing this down, which you should, you won't be able to write everything down word for word, so you have to learn to summarize it, and that's okay. This PowerPoint is available on the OneNote, along with and so it's there. It's there if you want to see this again. Plus, I'm going to post this on YouTube. So, all right, every spinning electron is a tiny magnet. Since all atoms have spinning electrons, why are not all atoms tiny magnets? And you might notice some of these questions are also on the review guide. But why is that? Well, the reason is that what I was talking about. Electrons spin in opposite directions, and in most atoms, you're going to have every electron that is spinning will have a partner that is spinning in the opposite direction. And even though they individually will have a magnetic field because it's a moving charge, since they're moving in opposite directions, they're going to have opposite magnetic fields, and they will cancel each other out. So that's why most atoms are not magnetic. So what's so special about iron and nickel and cobalt and a couple others that we're not worried about? What makes them tiny magnets? Well, they're not paired up. Simply put, they don't have a partner. There's one electron that's spinning all by itself, and nothing's canceling it out. Okay, that's basically it. So in iron and nickel and cobalt, they each have a electron spinning without anything canceling it out. So it has that magnetic field, and it stays. Okay? All right, moving along. What's a magnetic domain? This is definitely a vocab word that you should know. Okay, if there was a vocab list, this would be the one thing on the list. A domain, a magnetic domain. What is it? Well, when you get all those atoms spinning or having those electrons that are spinning around, every iron atom, for example, is a little magnet. What happens is some of those iron atoms line up. It's almost like if you look at an entire school building, everybody in this classroom is facing the same direction. That's a domain, kind of. Not a magnetic domain, but it's a domain. You go to another classroom, though, and they might be facing all a different direction. You go to another classroom, and they might have groups of students and desks facing different directions. But that's what a domain is. It's a group or a cluster or whatever you want to call it of aligned iron atoms or cobalt or nickel or whatever is a magnet. Okay? That's what a domain is. So why do some pieces of iron behave as magnets while others do not? Hopefully you know the answer, but you don't have to say it. And the reason is, in most iron, nickel and cobalt, they are randomized. They are all, like the domains are facing weird directions, random directions, and overall they cancel each other out. Okay, it's like this classroom, we're all facing east. There's another classroom where everybody's facing west. We would cancel each other out, facing the opposite direction. But in magnets, all the domains are facing in the same direction. And there's like in the notes are linked on the OneNote as well. If you look on the notes, you'll find like a little diagram. It looks just like this, except all the arrows are pointing in the same direction. That's it. So that's what a magnet is all about. All those domains are pointing in the same direction. All right. Domains. Got it? Good. Stop me if you got questions. All right. Now, this is a long story. It's a lot to write down, so we'll just kind of summarize this. A piece of iron can be induced or forced into becoming a magnet. For example, I showed you how I took a magnet and I was able to force a screwdriver to become a magnet. Okay? That's forced. What happened? Why is that possible? Well, it'd be like if Mr. Hallahan, the principal, came around to every single room and was like, all right, today all the desks are facing to the west. All of them, in all the rooms. And so all the little domains, all the little classrooms, we'd all have to turn our desks face to the west. And in that situation, Mr. Hallahan would be like the magnet, and all the rooms would be like the screwdriver. And basically that's what happens, is the magnet forces all the domains to line up in the same direction. Okay? Kind of what I wrote up there. Kind of. But you get the idea. So Mr. Hallahan is the magnet. The whole school is the screwdriver. Mr. Hallahan comes around and says, we're all facing west. Well, we're going to all face west. And now we are all aligned. And we are a school magnet or something. Okay, this is one of those things where I mentioned it, but I want to make sure it is clear. Why will dropping a magnet or heating it weaken the magnet? Okay, to put it another way, and if I want to just use H's, hitting or heating a magnet will weaken it. Okay, there's two ways to weaken a magnet. Heat it or hit it or drop it. Why?
Because it basically shakes up the electrons so that they're not all in the same domain.
Exactly. It shakes up all the electrons, all the domains, so they're not all facing the same direction anymore. I use the word that I use, like now, this is the only time in the entire year I'll use the word jostled, but I don't know. But yeah, it shakes them up. It jostles them up. If you hit the magnet, it's going to be like boing, and then they're suddenly not all pointing in the same direction. If you heat something, you're adding energy to it, and all atoms like kind of jiggle a little bit anyway. So if all the atoms are jiggling anyway, and you add a lot more energy, it's like giving a bunch of kindergartners a bunch of sugar. Like you could try to get them to line up, and they might for a few seconds, but good luck with that. It's not going to last very long. There's too much energy involved. So hitting or heating a magnet will weaken it. Got it? Pew. Good. All right, this is just a review of that underlying principle. What causes a magnetic field? Well, you can see, hopefully you know, the answer is not moving. Okay, yeah. The answer is it has to, so this again, we already said this, but I want to make sure it's clear. Moving charges causes a magnetic field. Moving charges causes a magnetic field. So, related to that, what must a charged particle be doing in order to be affected by the magnetic force? To put it another way, to illustrate this question, think about what I showed you yesterday. I had that giant magnet, and I set it up so that the magnetic field was facing like this. The magnetic field was aligned this direction. It was out of the screen toward you. Then I held that coil of wire so that the current, the wires, was going to be sideways like this. So the magnetic field was like this, the coil of wire, the current was going to go this direction, 90 degrees to each other. Not only that, But if I just held the wire in the magnetic field, did the light light up? No. What did I have to do to get that to light up? I had to move it. And not only that, I had to move it perpendicular to everything else. So the key word is moving. The secondary, but also minor, sort of important, is everything has to be perpendicular. That's why we get the left-hand rule where everything is perpendicular. Magnetic field, one direction. Current, perpendicular to that. Motion or force is perpendicular to that. Okay? That's the idea there. Everything is perpendicular. All right. It has to be moving. If it's not moving, it doesn't work. Speaking of moving along. What kind of field surrounds a stationary electric charge? So if I go, this is like unit 6 stuff, right? Like we have a charged object. What kind of field surrounds it if it's not moving, stationary? You have an electric field, okay? Again, we've talked about this. Why am I coming back to it? Well, because everything sort of has been building up to this. Like we had to know about that in order to know about other things, including magnets. So what about if that charge is moving now? And this is why it's important. When the charge starts to move, what's the source of all magnetism? Moving charges. So if it starts to move, I want to make clear it does not lose its electric field. It keeps the electric field, but now it also has a magnetic field around it. Okay? Was the magnetic field there in Unit 6 and Unit 7 when we talked about this? Yeah, but I didn't bring it up because it wasn't time yet. Okay? But I wanted to make sure that you know that the electric field doesn't go away just because it starts to move. You keep the electric field, and if it moves, you gain a magnetic field. Cool. Going back a little bit, why, and this is kind of maybe from the review guide, why can metal or iron be made to behave as a magnet, but wood cannot be? What does iron have that wood does not have? And that's that D word again. Okay, iron has domains. Iron has domains. Wood does not. Wood's got the electrons that cancel out. They don't have any domains at all. They cannot be made. Wood cannot be made into a magnet at all, ever. But iron can. What happens when you break a bar magnet? What do you get? Two magnets. That's it. You get two magnets. Okay. Two full magnets, north and south. Remember, you cannot separate north from south, so you get two magnets if you break a magnet in half. Okay, which one group tried on accident, of course. But yeah, you got two magnets, and yeah. So anyway, I could talk a lot, but I don't have time for that. So let's move on. This is something that I briefly touched on, but didn't enough. So I want to make this one clear because this is on the review guide and you're going to see a question like this on the test. The Earth is a giant magnet. Why? Well, it's not magnets in the ground. If there were magnets in the ground, there wouldn't be enough of them and they'd be all scattered around and randomized anyway and they wouldn't work out. The most common wrong answer is B. It is not that's, if you think about it, it's a little cartoony to picture just a giant bar magnet in the center of the Earth. That's not the case. So it's not the core of the Earth. So then you're like, well, it seems like the answer must be D because this seems ridiculous, but it's not. It's not the Earth's rotation because we got moons and Mars and other planets that rotate that don't have a magnetic field. And the reason Mars doesn't have a magnetic field, even though it's rotating, is because it has a solid core as far as we could tell. So all the evidence seems to support the claim that the flowing magnet, which kind of makes sense if you think about it, it's moving. There's probably lots of stuff in there, charged, whatever. So this is the prevalent theory, and all the evidence seems to point to this. There's no reason not to think that this is not the case. No reason to think this is not the case. So I'm saying it outright. Right now, it seems like flowing magma under the Earth is the source of all the magnetism, like the magnetic field around the Earth. Got it? Flowing magma. I wish I could get into more detail, but that's kind of like not. It's just sort of a. That's the answer, and we can move on. We can talk about it later, but not until after the test. All right, here's one that is easy to overthink. Which three can be magnetized? Can copper be magnetized? No. Can iron be magnetized? Yes. Cobalt? Yes. That's that weird one. Gold? No. Lead? No. Nickel? Yes. That's the other one. And then aluminum? No. Okay. So remember, like I said, this is the easy one to just like, oh yeah, I got that. And then it's easy to overthink it or underthink it. So make sure you are rock solid with this. Okay. So at some point, write those three things down without looking at the notes. All right. Just to make sure. Because it's an easy one to think you got. And then when it comes to it, it's like, oh crap, I forgot. Is it copper, cobalt? Okay. If you were to describe the shape of a current carrying wire around the shape of a magnet around, read it. The shape of a magnetic field around a current carrying wire, what would you describe it as? Good. I see some of you guys going like this. Perfect. Yeah, concentric circles is probably the most common way to describe it. There's a similar picture on the notes document. So if a current carrying wire is bent into a loop, why is the magnet field so much stronger on the inside the loop compared to the outside? What's going on the inside? Well, they overlap. They overlap when you do that. That's why it's so much stronger. If you put a nail in there, it makes it even stronger, which I showed you yesterday with that ring launcher. So they overlap, concentric circles. Okay. Okay. So now we get to it, the hand rules. We got two pictures here, and the right-hand rule. It gives us the magnetic field, and it wants to know the direction of the current. Okay. Right-hand rule. There's no force involved, so we're going to use just our right hand. And the idea with the right-hand rule is we use our fingers to curl. We curl our fingers to indicate the direction of the magnetic field. And then whatever direction our thumb is sticking out, that's the direction of the current. So for this first one, it seems to be curling around this way. So I'm going to curl my fingers around like this. And when I close my fist and stick out my thumb, then that tells me that the current is going up. For this one is the magnetic field going around this direction. And so if I take my fingers and I curl my hands like this, that direction, and my thumb pokes out, it's going into the screen. That's the right-hand rule. Now, there is another clue here, that little X, which won't be there on a test. That's the symbol for it going in. You might have noticed that, but just confirmation. So yeah, that's it. So whatever direction the magnetic field is, you curl your right hand. That'll tell you the direction of the current. Your thumb will. And then there's this one. Okay, this might be the hardest part of the test. Then that's okay. That's fine. Fair enough. All right, left-hand rule. Everything has to be perpendicular to everything else. So I start with the L, and then I stick my middle finger out to be perpendicular to that. So everything is 90 degrees to everything else. And then I remember the FBI. F is force, that's my thumb. B is the magnetic field, that's my pointer. I is current, and that's my middle finger. FBI. So then, this one shows a charge moving with the velocity to the right. So a moving charge is a current. That would be my middle finger. So I'd point that to the right. And then it enters this B. It enters this square where there's a magnetic field, but it's blank. I don't know what direction the magnetic field is pointing, but I do know that the path of my charge suddenly got pushed downward, forced downward. And since it's forced downward, that's F, that's my thumb. So while my middle finger is still pointing to the right, I'm going to rotate my hand. It's not easy to do, and that's how you know you're doing it right. So that the force, the F, is downward. And that leaves it with the answer of coming out of the screen. And yes, it will hurt. It will be uncomfortable, I should say. Okay? Something that, all right. Okay. Here's another one. I just want to explicitly say the answer to this is a lot easier if you know the magnetic field is strongest closest to the pole. Knowing that the magnetic field is strongest closest to the pole, which of these is going to be strongest? B. B is closest to the pole. Even though C is closer to the magnet, B is closer to the pole. And then for the next one, you kind of had to do like a little like measuring. So A is like a hand and a half away from the pole. C is like a hand and just a little smidge more. So I guess C is going to be our next answer. And then A and then D. Magnets are strongest closest to the pole. Remember that. Strongest closest to the pole. Okay. Almost done. Imagine, mentally draw the magnetic field lines. Does it look like that? No. No. Does it look like this? No. A little bit. They're coming out the middle, and I just got done saying the middle is the weakest point, so that's not it. No. All right. It's my word drawing. It's like word art, but yeah, it's coming out the ends, and yeah, that's essentially going to be what it looks like. Good. All right. Two magnets. Is it going to look like this? No, they don't overlap like that. Better. It's not complete, but it's better. Okay. And finally, I'm going to leave you with this. This is my last slide. It's comparing an electromagnet, a motor, and a generator. And I'm just going to put all these up, and then you can take a picture when I'm all done. If you want, I'll be very brief, though. Electromagnet, it's used to sort metals and move pieces of metals around. The parts, think about last Friday, iron core, a coiled wire, and a battery or a voltage source. You can make it stronger by more turns on the coil or applying more current, or both. For a motor, it's something that rotates a shaft. Anything electrical that moves in any way is this. The parts are, you built one on Monday, coiled wire, permanent magnet, and a battery. You can make it stronger by adding more turns to the coil, apply more current, or a stronger magnet. The generator, you didn't build one, but you saw one in the simulation, and I showed you some yesterday. They generate electricity. Coil wire, permanent magnet, something to turn the coil or the magnet. In my case, it was cranking the thing with my hands. And you can make it stronger by adding more turns to the coil, turning the coil faster, or having a stronger magnet. And remember that motors and generators are opposite.